Welcome to another unit in business mathematics. This time we're going to talk about integration and in particular about the so-called substitution rule of integration. We're going to talk about this in the context of four exercises, which here are basically just calculate the following indefinite integrals, which are the integral over 5 times exponential function of 4x, the integral over x squared square root of x to the power of 3 minus 3, 6x squared times exponential function of x to the power of 3, and finally, in parentheses, x plus 5 to the power of 6. Well, let's take this one step after another, starting with the easiest of the four exercises here. Easiest because, well, if we take a closer look in this regard, even if we have exponential function of 4x, we might directly come up to the solution of this integral without having to use any substitution formula whatsoever. However, I want to use this example to just illustrate the idea of what substitution is all about. And well, the real problem here is the 4x. So actually we want to replace the 4x with a new variable, let's call this u, because the exponential function of a variable u we can easily integrate. The exponential function of 4x, not so much. So what we can state here is we want to substitute 4x with a function u. To do this, we however have to impact the rest of this expression as well, because we will no longer be working with the variable x, but with the variable u. So we would have to replace the dx by a du as well. Okay, so if we do this, if we perform this substitution here, we could use any of two approaches. The first approach would be that we imagine to need in front of the expression where we do the substitution this first derivative of the substituting function. So we wouldn't need a 4 here. As we have a 5 here and not a 4, what we can do is, first off, we see this here, we pull the 5 in front, the 5 which we don't need in front, and then we expand with an artificial 1, meaning we actually expand by 4 divided by 4. That's the 4 we actually need at this point. And if we have 4 divided by 4, this is actually 1. So this will not interfere in the result. However, I only need the 4 here from the denominator. So I pull the 1/4 also in front of the integral, giving me this. So that here, this expression actually looks like first derivative of u, function applied to u. Or rather, derivative of function applied to u. And that's more or less how the derivative of the chain, or in regards to the chain rule, looks like. So what we do here with the substitution is reverse the chain rule for derivatives. Okay, in practical terms, what we will do here is we will replace 4x with u, dx with du, and we cross out here the first derivative of u, making it look like this. That's actually the substitution rule. You could, however, imagine this slightly different as well. What you could do instead is, if you decided you wanted to replace 4x by u, then you need to replace dx by du, and then you could simply divide this expression here, this expression in the integral, by the first derivative, which is here 4. So in the end, it's the 5 derived by 4. Will give you exactly the same result. Okay, once we did this in either of the two ways, we need to get the integral of exponential function of u, which incidentally again is exponential function of u, giving us here the result again with a plus c. And well, this is still in relation to u. We need this in relation to x. So what we do here is we resubstitute. So we again take this definition here and instead of u write 4x, making it look like this. And then we are actually finished. So here is decide what you want to substitute, get its first derivative. Either make it look that the first derivative is multiplied with this expression, or simply divide the whole expression by the first derivative, hoping that it becomes simpler. So that was the first introductory example. And well, here it was relatively straightforward to know what we need. In part B, this might be a bit more complicated. However, if we take a look here, the critical point clearly is the root. So to make this look easier, would be nice if we can have here a very simple root expression. Like for example, square root of u. So it would only be prudent to substitute x to the power of 3 minus 3 with u. Then what we either need to achieve to be here would be the first derivative, which is 3x to the power of 2. Or again, as I said, we can simply, when we replace this with u, this with du, divide by this expression. In either case, if we want to have 3x squared, well, we're halfway there, we're missing a 3 here. So again, we can expand with an artificial 1. So write 3 here, write 1 divided by 3 in front. This works with any numbers. This does not work with any axes, so not with any variables, but this works with any numbers or constants. So we prepared this. Then instead of the x power of 3 minus 3, we write u. Instead of dx, we write du, and we divide here by the first derivative of u. Crossing this out, leaving us with this expression. 1/3 integral of square root of u du. So either you learned a rule for the integral of square root of u, or, well, we could write this as u to the power of 1/2. Now we can simply apply the rule we know for working with polynomial expressions. So variable to the power of n. This means here we integrate by increasing the exponent by 1, giving us 1.5 or 3/2. And then we multiply with the inverse, or we divide by 1/2. So multiplying with the inverse is 2/3, which is the inverse of 3/2. Together with this 1/3 we have from in front here, we get 2/9 u to the power of 1.5. Well, there's still something to do, because first we need to use this for the resubstitution, and then we can write this. Well, first off, by simplifying the expression here and rewriting this as a root. So first we do the resubstitution. Instead of u, we again write x to the power of 3 minus 3 to the power of 1.5. Here we get 2/9. And well, this is 3/2. So something to the power of 3/2 means square root, that's the divided by 2, to the power of 3. So that's the more scientific way of writing this expression. Well, that was done, everything for part B. So we can continue with the third part. In part C, we have this function, which looks pretty similar to what we had before. First off, we again have here something which is reminding us at least a little bit of the derivative of this. And well, here, this is actually the function which annoys us the most, because exponential function of x we could easily integrate. Exponential function of x to the power of 3, we cannot. So this actually motivates to use, for the substitution, a replacement u, which is just x to the power of 3, and has the first derivative, 3x squared. Then we could simply divide this by 3x squared. Well, this would leave us with 2. Or we try to make this look like this one here, which we could also easily do by simply splitting this up into 2 times 3 and pulling the 2 in front of it. And it's actually the second way we use here. So make the part in front of the exponential function look like the first derivative by pulling the 2 in front. Then we can replace x to the power of 3 with u. We can replace dx with du. That's here the part. And we divide by 3x squared, getting rid of this part. Okay, then the only thing left to do is get the integral of exponential function of u, which, well, obviously that's why we did this substitution, is again exponential function of u. As we are done with the integral here, we put a plus c in the back because it's an indefinite one. This is more or less the primitive. So we need to conclude the resubstitution, so replacing u with x to the power of 3 again, giving us this result. Well, that's then everything there is to the third part, as we cannot simplify this any further. We can skip then to the fourth and final part of this exercise, and here with the function x plus 5 in parentheses to the power of 6. Obviously, we could calculate this and then do this step by step by simply using linearity rule and the rule we know for polynomials. However, this would be a quite tedious work to first get here to the power of 6 of this expression. So it would be a bit easier if we can find some kind of roundabout way. Well, the roundabout way can be found if we just think about this critically, because what is annoying here is not the to the power of 6, but the fact that it's not x to the power of 6, but x plus 5. So if this were simply a normal function like x to the power of 6, we could easily get the first derivative. The integral. So what we do instead is replacing the substituting here the x plus 5 with a normal single variable. So the substitution here is happening with u equal to x plus 5. The advantage, the first derivative of this, that's actually 1. And we already have, even if we didn't write this down, a 1 in front of the expression here. So we could simply substitute this, giving us here integral over u to the power of 6 du. And from this, we can easily get the integral as 1/7 u to the power of 7 plus c. Leaving us here only with the resubstitution, so meaning replacing the u again with x plus 5. And well, I hope you agree this is usually much faster, much easier than first having to calculate this whole parentheses at once. Well, that's then everything there is on this unit in regards to using the substitution rule. As I said, there's actually 2 ways to apply this. Either try to make it look that the first derivative already is here in front, or just say, when I do the substitution with those 2 parts, I divide by the first derivative. Both things actually lead to the same outcome. Well, then, as it concludes this exercise, just say goodbye and see you next time.